Good evening, everyone. Welcome to week 7 problem solving session for Analog Electronic Circuits course. So, in today's session, we'll be talking about differential amplifiers. Before that, am I audible clearly to everyone?
Yes, ma'am.
Okay, so let's begin. So, in today's session, we'll be talking about differential amplifiers. So, till now, what we have seen is there is an amplifier where we give input and we get amplified output, correct? So here what happens, let's say in your input, now for the same amplifier, in your input, there is noise added. From some source, there is some noise which enters your system. So what will happen? Your output will be actually amplified input plus noise, correct? So what happens is these amplifiers amplify the noise in the same factor as that of your input. But is there any chance that we can like neglect this noise or remove this noise and get the amplification of only input signal that we are providing to the system? So that is the idea. That's where people thought of like using, okay, so let's say if there is some black box, right? There we have two inputs, input 1, input 2, and we'll get output. So here input 1 is such that input plus noise, input 2 is such that it is input 1, input 2 plus noise. Now here the noise is of similar order, like noise is same. So let's say it is appearing through similar kind of disturbance, okay? So what we are giving to the input of this particular system is input 1 okay. So the actual input is input 1 minus input 2 is the actual input to this amplifier. Okay, this is a new type of amplifier. So now when you do this input 1 minus input 2, what you will observe is you will have input 1 plus noise minus input 2 plus noise. So actual output turns out to be input 1 minus input 2. So if you observe, you have differential input to the system, like you are providing a difference of two inputs to the system, and your output will come out accordingly. So this particular type of amplifier is known as differential amplifier, differential pair or differential amplifier. Now this can be further like divided into two types. That is, so for differential pair, your input is actual input is difference of two inputs. So you will provide differential inputs. Why? Because you want to remove the noise which is present. Now, depending on what type of output you will get, you can either get single-ended output or you will get double-ended output. So When there is single-ended output, that circuit we call as OTA, and for the double-ended output, we call it differential amplifier or differential pair. Now, how does this differential amplifier, differential pair circuit looks like? So we know that from MOS amplifiers, we get best inputs, like best magnification from CS configuration, right? CS configuration gives us best results with respect to resistances and everything. So your OTA or differential pair, differential amplifier, they are designed based on these CS amplifier based circuits itself. So first of all, if I draw an OTA, it looks like so. This is how your OTA looks. Now, let me quickly draw the differential amplifier as well. Okay. So, if we observe these two circuits very carefully, we can see that these two are similar circuits. Only what is different in these two is that, yeah, what is different is, first of all, if we look at the differential pair, so in this differential pair, Yeah, in this differential pair, there are two inputs. As we can see, one is V in 1, another one is V in 2. And there are two outputs, V01 and V02. So actual input, if we talk about in this particular circuit, is V in 1 minus V in 2. And actual output is V0 1 minus V0 2. Now, in the second circuit, which is in OTA, this is a single-ended output. So here again, the input is V in 1 minus V in 2, and actual output is V0. So here, as we can clearly observe, that these particular transistors are connected back to back, but in form of like they are basically CS amplifiers, right? Because the input we are providing to gate and output we are taking from the drain of the transistor, as this is gate, drain, source, drain, source, gate, source, drain, drain, gate, source. Okay. So here, if you observe very clear, we can observe something very clearly that any input state, since it is a differential input that we are providing, so any signal, let's say if you provide two same kind of signals to your amplifier, then those signals will be eliminated by this, and you will not get any output. So from there, we say that there can be two types of input. One is common mode input, and another is differential mode input. So when we say common mode input, what we basically mean is V in 1 equal to V in 2. Okay, and when we say differential mode input, it is input is V in, so these two are not equal basically. V in 1 is not equal to V in 2. You can understand like that. So when there is common mode input provided to either OTA or differential amplifier, we will get zero output. So ideally we should get zero output. That should there should not be any amplification at all. But practically we do get some signal, but it is so small that it is negligible. So yeah, so that is common mode input. And when we give two different inputs, V1 and V2, the output will come in terms of difference of V1 and V2. So it will be V1 minus V2, with which will be amplified by the factor of A, that is the gain of the amplifier. Now the question arises, okay, where would we want like differential amplifier and where would we use OTA, correct? So let's say you want to derive a load based on output current. So in that case, you can use OTA as it can provide current to you. But if you want your output, so let's say there is some error which arises in the circuit itself after input. So maybe let's say that's thermal error or something, because of which there is some noise in the output. Now, if the output is also differential, so what will happen, since the circuit will provide same noise, right? Same amount of noise to both the output terminals. So the differential output circuit will basically eliminate that noise. So it is even like it is even better circuit, we can say. So, if you have a differential output or double-ended output circuit, so basically in double-ended output systems, you can get output in form of potential difference. But if you want to use currents, so you will go for OTA. So that is how we basically differentiate the uses of like OTA or amplifier. Okay. Now, so based on this basic understanding, let's dive into uh, the problems and we will understand things even better. Now, coming to the first problem. So, in this problem, see here it is given that it is a MOS-based differential pair. Both MOSFETs are perfectly matched. So, here VT is zero point 0.5 volts, Kn is 4 millisiemens per volt, lambda is 0. The differential gain of the circuit is how much? So here, first of all, the idea is everything, every component in this particular circuit is equal, right? Both the transistors are matched, all the resistors are matched. So what we will do, we will try to break this particular circuit as well. So we will try to break this 10 ohms also into equal parts so that we can have a symmetric circuit. And as I told you last time also, when we have symmetric circuits, we can analyze half of the circuit and comment on that, like from there we can deduce the results. So analyzing half circuit is sufficient. So how would the resultant circuit look like? This is 5K, 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 5K. Okay, so here what we will consider is first of all this point 0.8 amp, point 0.8 milliamperes current which is flowing. It will be divided equally among both the branches, correct? So here this branch will have zero point 0.4 milliamperes of current. This branch will have zero point 0.4 milliamperes of current. And now if we want to find a gain of the circuit, so basically we want the AC gain, right, for the signal. So for AC gain, we will take one half of the circuit. So this particular half, yeah, this half circuit we will analyze, okay? So half circuit will look like, since it is an AC analysis, we will put this part to AC ground, that is your VDD to AC ground. We will say that since the circuits are completely matched, so the potential at this point should be zero. Because let's say some current is coming from this branch, some current is coming from this branch. So at this point, the currents will nullify each other. So the center point is almost like it will have a grounding property. Now, talking about this current source, so since it is a current source and it is a like independent current source, so the current through the system will be constant, it will never change. So the potential at this point is also constant. So it will almost behave like a DC point. So that's why this point will also go to AC ground. Now, based on this, we have to analyze our circuit. Okay, so we know that gain for CS. So this is basic CS configuration, right? Yeah. So in this CS configuration, we know that gain is minus GM into R out or Z out. And we know that for this particular type of circuits, the gain comes out to be minus RD parallel RL upon 1 by GM plus RS. So this is for the circuit when you have source resistance. So when there is a source resistance, how will your output look like your gain look like? And this is the point where you're looking for your V out. So now here LV is 5 minus 5K parallel 5K. These two, yeah, so these two resistors are in parallel as they will come in parallel when we draw the small signal model. So those two, then it will come by 1 by GM plus RS is 50 ohms. So that is AV equal to minus 2.5 K by 1 by GM plus 50 ohms. Now for GM, we know the formula that is root under 2 mu CX divided by L into ID. So it is given that we know like ID is zero point 0.4 milliamperes for this particular branch. Here the ID that is flowing is zero point 0.4 milliamperes. So ID is zero point 0.4 milliamperes. Kn is given which was 4 millisiemens per volt, which is neon Cox W by O, that is 4 millisiemens per volt. So the GM will be root under 2 4.4. So GM comes out to be 1.789 milliamperes per volts. So with this GM, when we substitute, the AV that we get is minus 4.105. Okay. Now, as we mentioned that there can be two types of inputs, so we can have gain also of two types. So again, maybe I'll show it here only. So when we talk about gain in differential amplifier, the gain is also divided into two types, that is common mode gain and differential gain. So you give your common mode gain. So this is known written as ACM and this is written as AD. And how do you judge whether your differential pair is good or not? It is based on common mode rejection ratio, that is CMRR, which is basically AD upon ACM. So ideally, what we want is CMRR to be infinite. That means your ACM should be zero. So the common mode gain should be as low as possible. So while designing your differential amplifier, the parameters you are given is differential gain, that is the gain that you want from your differential amplifier for differential input, and then your CMRR. So your differential amplifier it's judged based on your differential amplifier's CMRR value. The higher the CMRR value, so basically your the amplifier is that good in rejecting the common mode or signal or basically the noise. Okay. Now ACM is given by V out upon V in by 2 and AD, that is differential gain, is given by V out upon Vn minus Vn1 minus Vn2. Okay, so this is how we find the ACM and AD by 2. So how does this come Vn? So it is like Vn1 plus Vn2 by 2, the average of inputs. So that's why this ACM denominator comes out to be Vn by 2. So ideally your CMRR is infinite. Practically it should be 80 to 120, 180, sorry. Yeah, 180 to 120 dBs. Okay. So this is the CMRR that you target for. So if your CMRR is more than 120, then you will be able to use that particular differential amplifier very satisfactorily. So that is the idea. Now, moving on to the next problem. So is this clear? Basically, what is an differential amplifier? How do we use them and everything? Hello?
Yes, ma'am.
Okay. And if you want to know the example for differential amplifier, basically all of you must have heard of op amps, right? And you must have seen that op amp. So we have this triangular device, right? Where we have two inputs and one output. So this is basically differential amplifier. So op-amp is a differential amplifier, right? So when we design an op-amp, we start with this differential pair. We do some other, like we do add some other stages, and then this particular op-amp is designed. But the input part that you observe with two particular input terminals that comes from this differential pair only. Okay. So yeah, now let's move on to next problem. So in this problem, as you can see, again there is a differential pair where the input VCM is applied, and consider the MOS differential pair in this circuit with VCM to be 1.7 volts. I naught is 3 milliampere. ID is 0.633 kilo ohms. VT is zero point 0.5. So what is the minimum allowable supply voltage if the transistor must remain in the saturation? Okay, so supply voltage means VDD. So here we have to find the value of VDD such that for the given currents, your transistor, first of all, it has to be in saturation, and also your yeah, so minimum value for which your transistor will carry so this is 3 milliamperes. So that means each transistor would carry 1.5 milliamperes. And based on that, and also it is in saturation. So what is the voltage that you would require to use this circuit? So again, by analyzing the half circuit, we know that VDD is being distributed as ID by 2 into RD. So that is the drop across this particular RD resistor plus VDS, correct? So this VDD is being used as a drop across RD and drop across this particular transistor. Considering that since it is a ideal like current source, so there is no drop across it. So based on that, if we observe, so what is the VDD that is required? We can write it in this form. So VDD is ID by 2 into RD, so that is basically 1.5 milliamperes into RD was 0.633 kilo ohms plus VDS. Now we know for saturation, VGS minus VT should be less than or equal to VDS. So that means VGS minus VT should be minimum equal to VDS to start your like it is the limit of your saturation, right? Saturation limit. So based on that, now here we know that VCM is already given. That is 1 point. In this particular circuit, VCM is 1.7 volts. And as I said, like we are considering that there is no drop across it, so maybe we can say like this is ground point. So no potential is dropped across after this point. So that makes my VGS to be equal to 1.7 volts, correct? Which is also equal to VCM. And VT is zero point 0.5. So VGS minus VT will become 1.7 minus zero point 0.5. So that is 1.2 volts. This will be VDS. This is like the limiting condition of VDS. So the limiting VDD will turn out to be this value is 0.95 if you calculate plus BTS. So this is 0.95 plus 1.2, that is 2.15 volts. So the minimum VDD that you would require to keep your circuit and saturation is 2.15 volts. Is this clear how we solved this problem? Any doubts in this problem? Okay, if you have any doubts, you can unmute yourself and ask, right? If you don't unmute, then I'll consider that you understood this. Okay?
Ma'am, I have a doubt.
Yes.
In case if we want to find the maximum VDD, how should we proceed, ma'am?
See, there is no condition for maximum this, right? So we know that the minimum
Ma'am,
you
can you repeat? Sorry for the disturbance. Can you repeat, please, ma'am?
repeat this particular problem.
Yes, ma'am. Because in the given assignment, I think it is a little difference, the question and all.
Okay.
I think you are solving that assignment 7 or
No,
assignment
so
7 only
I
you are
want
trying,
to. No, no, this is not the questions from the assignments. So I'm not allowed to solve the
You are
questions
commonly
which
you
are.
are taking.
Yeah, yeah. So we are not allowed to solve the problems from the current assignment. So
Anyway,
current assignments.
ma'am.
Yeah, yeah. So I'll repeat this, but these are
Once again
similar
repeat, please,
pattern
ma'am, from the
problems.
beginning.
Yes,
Beginning.
yes. Okay, okay. I'll do that. So, anyways, to come back to the previous
Okay,
question, when there was this question that how to find the maximum values, correct? So, when we talk about
okay,
saturation, we
okay.
know the minimality, right? We know that VGS minus VTH should be less than or equal to, like, if VDS reaches VGS minus VT value, that means your saturation starts. But until where your saturation will go, that is not like we don't have exact value for that, right? You can increase your VDS until you reach the like punch through situation where your channel is completely gone. So those kind of things, but we don't use such high values anyways, right? So there is never a maximum value condition, because also there is another reason why we don't look for maximum values is because first of all we want to use this transistors, so we want to use them for low power dissipation, right? So we want to see, okay, what is the minimum power dissipation that I can like, or the minimum power that I can apply for to my circuit so that they can sustain and perform the operation that we want. We never look for the higher end because our priority is more on because the if we start looking for the higher end, it is basically cost the it increases the cost because the moment you increase the power, your cost increases. So we want to use less power. So that is also a reason why we have all the conditions for minimum values. Yeah, we don't have any expression for maximum value, like what could be the maximum value of VDS for keeping their circuit in saturation. We never have that because our priority is looking for minimum. That's why. Hope,
Okay, ma'am. Thank you.
yeah. Okay. So coming back to this problem, so as there was a doubt, so the question is we have to find the VDD. We know what is the current that is flowing through the circuit, and we know the potential applied to the gate, that is VCM, is 1.7. We know the VT to be zero point 0.5, and the current flowing through one branch is 1.5 milliamperes. As I said, these are um, symmetric circuits. We can have one half and analyze the one half and look for the answer. So based on that, in the half circuit analysis. And also, if you see under, there is this I naught. I naught is a independent current source. So considering that independent current source does not drop voltage from VDD, so we consider that at that point there is no voltage drop across your current source. So based on that, your VDD will be dropped across the RD as well as this VDS of your MOSFET. Correct? So I simply wrote down the KVL equation, that is VDD is ID by 2 into RD plus VDS. So this ID I should write it as I naught. So basically this is I naught by 2 and this is ID. So I naught by 2 is ID. Okay. So yeah, it is I naught by 2 into RD plus VDS. We know RD, we know I naught, so we can find the first term. Now we have to find for the second term, that is VDS, the drop across the MOSFET. So the drop across MOSFET for saturation, we know that VGS minus VDH should be less than equal to VDS. So that means VDS should be at least equal to VGS minus VT to start your saturation. So considering that condition, we have solved for VDS and we found out that VDS was 1.2 volts. And when we got VDS, we simply substituted it and we found out that the minimum, this is minimum VDD required is 2.15 volts. Is this clear?
Yes, ma'am.
Okay. Now let's move on to the next problem. So in this problem again, so we have to use the same circuit. Okay. So in this circuit, it is given that with RD, R naught, and I naught as defined earlier. So that means I naught 3 milliamperes, VT of 0.5 volts, RD is 0.633. Yeah, 0.633 ohms. The power supply voltage has been fixed to 5 volts. Gain of the input circuit or input device is 33 millisiemens per volt, and gain of the device used to make the current source is 66 millisiemens per volt. So what is the maximum input common mode swing that is allowed such that all the devices remain in saturation? Okay. So first of all, the thing is, when we talk about ideal current sources, there is nothing called an ideal current source. Okay. So all the current sources are designed. And in our terms, when we say we are using a current source, so basically we use a transistor or a MOSFET in saturation. We know because in saturation, it gives us a current source kind of behavior, that is constant current behavior. So that's why instead of I naught, what is actually present over here is a MOSFET. Okay. So let's say it is an N-type MOSFET. And yeah, it will be biased with some voltage, VA, whatever it is. We can easily find out this VA considering that we know the current, right? So this is the idea. So basically there is a transistor which provides us this current source behavior. Somebody's mic is unmuted. Can you mute yourself? There is a lot of disturbance coming. Somebody's mic is unmute. Can you mute yourself? Okay. So yeah. So the KN2 is corresponding to this transistor. This is, yeah, KN2 corresponds to this transistor, whereas KN1 corresponds to these two transistors. Okay. Now the idea is, okay, let's name them transistor T1, T2. This is transistor T3. Uh, Current through transistor T1 and T2 have ID equal to I naught by 2, that is 1.5 milliamperes, which will depend on Kn1 VGS
Ma'am,
minus. Yes.
have you changed the current source into a transistor, ma'am?
So current source is ideally a transistor. If you are designing a circuit, so we don't have ideal current sources, right? And we design all the circuits based on transistors only. In fact, the resistors that you are seeing here in this particular question, in practical case, these resistors are also transistors. So we derive the resistance from the transistors only. So at the end, your whole circuit is designed out of transistor. It's to make the designing easy, and yeah, so it's basically to make designing easy because you're using only single component. So here, when you see a practical transistor circuit, so we will come across them. There you will observe that all the components, say resistance, capacitance, and here in case the current sources, all of these are designed out of MOSFETs. Okay. So in practical scenario, your current source is actually designed of MOSFET. So that is what here also I mentioned, right, in the question. So first, the Kn of the input device is 33 Siemens per watt, whereas the Kn of the device used to make the current source is 66. So it was clear from the question that the current source is now not an ideal current source, rather it is a MOS device with the given Kn, that is 66 millisiemens. Is this clear? Hello?
Yes, ma'am. And what is Kn, ma'am?
Kn is basically we know, right? ID equal to Kn Vgs minus Vt whole square. So this Kn term basically, Kn
It is
by
a
2.
constant, ma'am.
Yeah, it's the constant, basic constant that we have.
I think it's a saturation current, yes?
No, it's not saturation current. Kn is the constant. Kn is mu and Cox W by
Yes.
L.
In some of the book, instead of Kn, they mentioned beta n.
I mean, yeah, so constant can be named in any form, but conventionally K is used, like Kn, K dash, some K. But when it is talked in terms of like with respect to MOSFET and MOSFET's perspective, whenever K comes into picture, it is this particular constant,
Okay, okay, okay.
which is dependent on device
And
parameters.
from this Kn, I think you mentioned, as you mentioned, the mu n. Mu n is the mobility, yes?
Yes, mu n is the mobility, Cox
It
is
also
the
has a standard
conductivity.
value, na?
Yeah, like it has some standard value, so depends on what temperature you are using. So there are a lot of factors, but while designing, you use certain values to solve the
Okay,
problems.
okay. In this, I think in this problem, they given the value of Kn1 as well as Kn2, so that only we don't bother about anything, yes?
Yes, yes. It's just
Yes, ma'am.
so rather
Yes, ma'am.
than
Proceed.
Yeah, so rather than giving you the values of each and every constant like mu, Cox, W, L, they have given it in form of kns to make the calculations
Okay, okay,
easy.
good, good. Okay, understood, ma'am. Okay.
Yeah, yeah. Okay. So let's move ahead. So first of all, now here, anyways, we know that for finding the currents, we know the constants, we know the VT, that is threshold voltage. What we need to find out it is VGS, that is gate voltages, right? So in transistor 343, it is said that it is in saturation. So for saturation, we know that VGS minus VT should be less than equal to VDS. So your VGS, and we know that I naught, that is ID2,
Ma'am, one more doubt,
is
ma'am.
yes,
Under the saturation,
yes.
VGS is far greater than VDS, na?
Under saturation,
Under the saturation, the
huh.
higher value of VDS is very high, na? The device goes to pinched up mode.
Yeah, if it is very high, like too high, then device will go to pinched off mode. But
Okay.
we don't have to go till that limit. So that's why we look for like minimum values possible.
Okay, ma'am. Okay, 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 okay.
Yeah. So from here, we know that for the minimum condition, we have like VDS3 is VGS3 minus VT. So VGS minus VT is also known as overdrive voltage. So just if you find overdrive voltage written somewhere, it is basically VGS minus VT. Okay, so just don't get confused. It is the term used for VGS minus VT. So, anyways, here, your this VDS3, if you observe very carefully from the transistor, is equal to, so this is drain source, drain source. So this is the drain terminal voltage, right? So let's say we are going to solve the half circuit. So that means VDS3 is actually equal to VS1, like the source voltage of transistor 1, correct? From the circuit that we are observing. So we can say that VS1 is equal to V overdrive 3, that is VGS3 minus VT, correct? Simply by solving the transistor, like solving this particular, by looking at this particular circuit, we can say like this. Yeah. Okay. So this is first thing that we found out. Now for transistor T1, also we will have VDS1 should be equal to VGS1 minus VT. So that means VD minus VS1 is equal to VG1 minus VS1 minus VT. So VD1 is equal to VG1 minus VT. Right? Or we can also write it as VDS1 equal to VG1 minus VS1 minus VT. We earlier found out this VS1, so let's substitute this here. So VDS1 is VG1 minus VGS3 minus VT minus VT. So that means VGS1 minus VGS3 plus VT minus VT. So VGS1 turns out to be VG1 minus VGS3. Okay. And VGS1 minus VT, that is V overdrive 1. So V overdrive 1 can be written as V overdrive 1 can be written as VG1 minus VG VGS3 minus VT minus.
Ma'am, I have a doubt.
Yes.
Why aren't we considering VG1 as VCM like we did for the previous question?
So here it is mentioned that RD, I0, and VT can be used as defined earlier. But it is never mentioned that you can use the VCM, right? Rather, the question is what is the maximum input common mode swing that can be used? So basically, here in this particular question, what you have to find out is VCM max and VCM min. So, what is the maximum VCM that you can apply to the circuit, and what is the minimum VCM that you can apply to the circuit so that your transistor remains in saturation? That is the idea.
Okay, ma'am.
Okay. Yeah, so VDS1 we found out. Now, if we look into this, so this we are simply looking into what all we can find out from this. So from VG1 can be written as this is VOV3. So VOV1 plus VOV3 plus VT is VG1. So considering that let's the VOVs are equal, that is VOV1 equal to VOV3. So the overdrive voltages across the transistors are equal. So from there we get VG1 to be 2V overdrive voltage plus VT as VG1, right? Okay. So now let's solve for VCM max and VCM min. VCM max. So the maximum VCM voltage that can be applied across the transistor such that it remains in saturation. So for VCM max can be given as VDD minus I0 by 2 into RD plus VT. So, the- okay, so VCM max is given by VDD minus I0 by 2 into RD plus VD. So this is basically where it is coming from is VDD equal to I0 by 2 RD plus VDS, where this VDS is replaced by V overdrive. So VDD is I0 by 2 RD plus VGS minus Vt. So from here, Vdt equal to I naught by 2 Rt plus Vg1 minus Vs1 minus Vt. So Vg1 is Vt minus I naught by 2 Rt plus Vt plus Vs1, right? But as we considered in previous question, like considering that there is no drop across this lower transistor, that is the current source. So that means this particular transistor is, or this particular current source is ideal. In that case, we said there won't be any drop across this particular area, right? And from there, we got Vs1 to be 0, right? From similar assumption, this has been turned to 0. So from there, the condition of maximum VCM, this is VCM max. So the condition of VCM max comes into picture. That is VDD minus I naught by 2RD plus VT. Is this clear how we came across this formula? So it is by using simple KCL, but here we have like considered that there is no drop across this current source, the no voltage drop across this current source. Depending on that, we get this condition. So by simply substituting the values, the value of VCM max that we obtain is 4.55 volts. Okay. Now, when we talk about VCM min, so the VCM min comes from this particular space. So this particular formula that we solved, right, based on VOV. So this will give us VCM min. So VG1, that is 2 VOV1 plus VT. So VOV is VGS minus VT. So VOV ID we know, ID is Kn VGS minus VT whole square. So VGS minus VT, that is VOV, can be written as root under ID by Kn. So VCM min is twice of root under 3 by 66 plus VT is 0.5. So from here, the VCM min that we obtain is 0.926 volts. And the difference between the VCM max and VCM min, we call it as ICMR. Okay, this is input common mode ratio or input common mode signal, ICMR. It is given by VCM max minus VCM min. So this will be 4.55 minus 0.926. So this input common mode range comes out to be This input common mode range turns out to be 3.62 volts with a maximum and minimum value of this. So basically, the idea is you can give your input, common mode input in this range to keep all your transistors in saturation. That's what we solved from this particular problem. Is this clear how we solved this? How we approached this problem? So first of all, while designing, if I talk from practical perspective, you know that threshold voltage of your transistor is fixed, but you can decide on your overdrive voltage, right? So overdrive voltage is in your hands. And based on your overdrive voltage, your VDS will depend. So from there, you can analyze. So is this clear how we found this ICMR?
Ma'am, can you explain it once again?
Maybe you can go through this problem as I have already solved this. So you have the solution with you. You will get the PDF and you can also look into the video because we have other problems also, right? Otherwise, we would be stuck in the same problem.
Okay, okay, yes, ma'am.
Yeah. So you can look into this through the document or you can rewatch the video as well. Because the more questions we will practice, the more idea we'll get, right? Otherwise, we'll be stuck on the similar pattern. That's it. So yeah,
Ma'am, all the problem, I think you have done so many assumptions. All the problems you have to do like this, or
yeah, it will depend based on problems, but the assumptions which I have
yeah,
taken are generic assumptions, like they
so
can
many
be
assumptions
considered.
you consider. Na?
Yeah, yeah. So it will
In
depend
in
from
the
problem
problem
to
only they mentioned some parameters only. You assigned so many parameters. Yeah,
yeah,
this
yeah.
is the way only we got to solve, or as per our own idea we can utilize.
I mean, so what happens is if you take reasonable assumptions to solve a problem, first of all, the
Oh,
problems will be easier for you to solve. And the
okay.
assumptions depend on you, but the assumption should be reasonable. So it should not be like you can take any assumption. Assumptions are based on some logics and some idea that we deduce from the system, right?
I think
So
you done three problems. All the three problems you done three problems. I think all the three problems you have to take the similar steps. Yes, like yes, you have to
yeah,
proceed.
almost.
You can
More,
able to complete the entire.
yeah, yeah, more or less you can do that. But that's what I'm saying because until now we were more or less considering that this last transistor as ideal current source transistor. Even here also, when I said my source voltage, that particular this point voltage is not changing, so it comes from that assumption only. But now,
Yeah,
when
yeah.
we are going for actual transistors, then I can never say, like, let's say my transistor is so small that this point I am unable to get an ideal current source out of that particular transistor. Then definitely the source potential over there will change. So, how we approach the problem will also change. But more or less, we can use these steps to solve the problems unless there is something particularly given in the question which needs to be attained. So, yeah, that's why I'm saying that maybe we can look into two, three more problems to get even broader idea like how to solve. But more or less, you can use this particular method to solve all the problems. It is okay. Am I clear? Okay. So hope I am clear with that. Moving on to this next problem. Here again we have Kn as 2.9 millisiemens per volt, Kp. Now see, until now we were using resistors, but as I mentioned, all your circuits are designed using MOSFETs. So here instead of drain resistor, you have PMOS transistors, right? So that's why you have Kn and Kp different. All devices have VT of 0.3 volts. Lambda of all devices. Now here the lambda factor is also coming into picture. So things will be modified based on this lambda. I naught is 0.16 milliamps. What should be R such that the differential gain of the circuit is AD is 34.7. If there is no unit mentioned, that means volt by volt. Okay? So, yeah. In this particular problem, again, GM is we will solve half of the circuit, and based on half circuit analysis, it is since it is a CS amplifier again, so the gain will be GM into Z out, the simple gain that we know, and ID is Kn VGS minus VT whole square, because we know that all my transistors should be in saturation to get amplification. And since there is no mention of this ideal current source being a transistor or not, so again we'll assume that this point is almost DC, matlab AC grounded. That means this point's voltage is not changing. And we'll again go to AC analysis. We'll also put this point to ground. And then based on that, we will have, so this is your ID, that is Kn VGS minus VT whole square. Now here Gm will be 2 root under Kn IT. So as you know, Gm is right. So this is Gm. So from here we know that Kn is given 2.9 millisiemens. The ID is 0.16 milliamperes. So as I have mentioned earlier also, that whichever transistor you are giving input to, the GM is calculated with respect to your input transistor. So the transistor from where you give the input, your GM comes from there. So that's why we are using Kn. Is this clear? So GM will be 0.96 millisiemens. Now, when we talk about Z out as at this particular point, so when we have Z out will be looking from this point. So from top and from bottom. So this P-type transistor will give us 1 by GDP. This N-type transistor will give us 1 by GDN. We discussed this last time as well, right? And then we have this R, so this particular transistor. So it turns out that Z out will be 1 by GDN parallel to 1 by GDP parallel to R. Now Lambda is given. From there, 1 by ZDN is actually R naught. That is 1 by lambda I naught by 2. Because the current flowing through this particular branch is half of I naught. So that's why it should be I naught by 2. Similarly, 1 by GDP is R naught. This is N, this is P. So again, it is 1 by lambda I naught by 2. Since same lambda for both NMOS and PMOS transistors. So Z out is actually R naught N parallel R naught P parallel R. So that is 2 by lambda I naught parallel 2 by lambda I naught parallel R. So Z out becomes 1 by lambda I naught into R by 1 by lambda I naught plus R. So this turns out to be 62.5 R by 62.5 plus R. So now we know that 34.7 is the gain, which is equal to 0.96 into 62.5 into R by 62.5. 62.5 plus R. By solving these two, we will get the value of R to be 85.7 kilo ohms. Okay. So it was rather straightforward. So we didn't have to do anything. It's simply GM into Z out, as we know for the CS amplifier. The basic gain that comes out is GM into Z out. So from there, we have simply solved this problem. I hope this is clear, this problem. Any doubts in this problem? How we approached this problem, is this clear? Okay. So if there are no doubts, let's move on to the next problem. So in this problem, now if you see this is an OTA, since it is a single-ended circuit, so there is a single-ended output. So it's an OTA circuit. Now here it is mentioned that this device has current equation in form of K VGS minus VT whole square 1 plus lambda VDS. So this is by using the channel length modulation equation. So here Kn is 4.34 millisiemens per volt. Kp Kp is not given since it's also not required. So anyways, lambda n is 0.2 volt inverse. Lambda p is zero point 0.2. Okay, so both are same only. I naught is 313 microamps. What is the GM of the NMOS device? Okay, so if I naught is 313 microampere, IT will be 313 by 2 microamps, correct? Because half of the current will flow through each branch. ID is K VGS minus VT whole square 1 plus lambda VT. Yeah. Here VT is not given this problem. Okay, so we know that GM is 2 root under k into ID, right? We used this in last question as well. So from there, we'll simply find the GM directly. That is 2 into root under 4.34 millisiemens per volt into 31352 microamperes. So GM turns out to be 1648.28 microsiemens. So basically, how you approach a problem depends on what are the things given in the problem. Like first we will try to see if there are things which are given in the problem that I can use directly without taking any assumptions. That is the best approach possible. Now, if you think there are certain things which are missing in the problem, which are necessary, you don't have other way in solving, then you will take reasonable assumptions and solve the problem. Like in this problem, if we say, so if we want to, let's say, go for by solving this ID and calculating the GM, it would have been a tedious process. And we also know there are, so nothing has been given, no VT, no VG, no VD, no S, like there is no voltage is provided to you. In this particular case, solving this problem from that approach, that is GM equal to dID upon dVGS, it will be very tricky. So rather than that, what we did is we used the formula directly that we have seen in the last problem. And by using that simple formula, we have calculated the GM, which was asked in the question. Is this clear? So basically, how you approach a problem depends on what are the uh, like what is given in the question and what is asked from the question. So at the end, it comes out it boils down to that. Now, in this question, it says, what is the R naught of NMOS and PMOS? So we know R naught we can directly write from lambda, that is 1 upon lambda ID. So that is 2 upon lambda I naught. And since lambda was same for both N and PMOS, so R naught N will also be equal to R naught P, and that is 2 upon zero point 0.2 into 313 microamperes. So from there, the R naught turns out to be 31.94, 31.94 kilo ohms. Is this clear? Okay, so moving on to the next problem. Question number 7. So what is the differential voltage gain of this particular circuit? So let's take this circuit. So again, since differential gain is always GM into Z out, okay? So if you know the GM, you know the Z out, you can simply calculate. So from here, if we see the Z out, here it should be 1 by GDN, sorry, GDP. From here, we would get 1 by GDN. These two will come in parallel. So Z out will be 1 by GDN parallel 1 by GDP, or R naught N parallel R naught P. So this should be R naught by 2, And GM we already found out. So the gain will be, that is 80 UP minus GM was how much? 1648.28 into R naught by 2, which is 31.94 kilograms by 2. So AD in volt by volt turns out to be 26.323 volt by volt. And the similar gain when we want to calculate in dBs, it would be 20 log 26.323. So which comes out to be 28.41 dBs. Okay. Okay. Coming to the next problem. So there were no
Ma'am, want
questions, right?
to show that slide, ma'am, before question 7th one?
Before 7? Okay.
No, ma'am,
This
7th one.
okay, only 7th one? Yeah. This.
Yes, ma'am.
Any doubts here?
Okay, ma'am. Okay, ma'am.
Okay, right? Okay. So moving on to the next problem. So the circuit is modified as below. Now here if you see, this input is dependent on this output. So this output and input have been related to one another, and VB being significantly large such that the device conducts current of I naught by 2. So it is, the device is conducting the same current R1. R1 is 8 kilo ohms. R2 is 5 kilo ohms. So this is how these two are connected. So we have to find what is the voltage gain V out by V in. Now, okay, so here in this particular circuit, there are two transistors, and here let's say this is Vn, so here it would be Vn dash. So now how would we find Vn dash? Is actually V out into V out minus V. R1 upon R1 plus R2. Now, talking from a small signal perspective, now neglecting the AC component, let's put this to ground. So V in dash will actually come out to be V out into R1 upon R1 plus R2. So V out by V in dash is R1 plus R2 by R1. So that is 1 plus R2 by R1. So V out by V in dash will be 1.625 volt by volt, that is 4.2 dBs. So this basically we have solved it very directly, right? But to understand this particular circuit, it's a very complicated sort of self-biasing kind of circuit. Okay. So here, rather than providing two inputs, what we are doing is we are only providing one input, and the other input for the differential pair or the differential input is being governed by the output. So for the solution, say we have solved this very easily, but now let us basically understand like how this circuit works, okay? Because
Ma'am,
it is very important
Ma'am,
to, yes,
ma'am, that V naught will be supplied to V in dash, ma'am.
sorry.
Ma'am, V out will be supplied to V in dash, or
So it's like it's a feedback circuit. Do you understand feedback? Feedback means when something from output is again given into input. So in this circuit, if you observe very carefully, so it's basically a resistor divider across V out, which has been connected to V in dash, such that some part of V out will be provided to V in dash, right?
ma'am, what is V in dash? It is an input connected one.
Yeah. V in dash is input, right? You have two transistors, this transistor T1 and transistor T2. These two are input transistors. For a differential pair, you should have given two inputs, right? To both the transistor T1 and T2. To T1, you already have the input V in, and to T2, you don't give external input like V in 2. Rather, you have connected your output to this particular point in such a way that some part of your output is already being provided to the input.
Okay, ma'am.
Okay, so we solved this
ma'am,
yes.
over here in the calculation, V naught by Vn, the answer should be 2.6. Final answer.
Answer should be 2.6.
Yeah, over here solved no? 1 plus 8 upon 5.
Answer is coming to be 2.6.
Yeah.
Oh, sorry, this is 5. R2 is 5, right?
Yeah, 5 8.
So it should be 5 by 8. Yeah, so 1.62 would be the final answer. But anyway, so this is something more like a shortcut. But actually, if we go on analyzing this particular circuit, it's a very complicated circuit, and it's one of an advanced kind of circuits where there is so where the input is being so output is being fed to the input. So it's like a feedback network. Okay. So now maybe we'll quickly analyze this particular circuit and understand how this circuit works. Okay. So yeah, let's quickly draw the OTF first. Okay, so let's say your Vn1 is Vcn plus delta. Okay, this is the input that you are providing. Vn2 is Vcn minus delta. So here we consider that again, since it is a direct like current source, we say that this point is fixed. Okay, and here the gate voltage is Vcn plus delta, and here the gate voltage is Vcn minus delta. So if you see your gate voltage, this point is fixed and it is at, let's say, Vx. Okay, so your source voltage for both the transistors are equal, but your gate voltage of one transistor is larger than the source voltage, right? So the small current I that will be flowing through this transistor, this is the AC current I'm talking about, okay, which is coming because of the signal. So this particular current, small current, is flowing through this transistor, which is because of this extra delta coming into picture. But now in this particular, so the DC current is I naught by 2, which is flowing through both the branches. This is equal and half half. Because of the small signals which are applied to gate, there will be another current that is small I, which will be flowing through these circuits and which will depend on these gate sources. Like gate, what is the potentials that you are, or the signals that you are applying to the gate, right? So the small I is flowing through this transistor T1, right? But you know in transistor T2, you have minus of delta I, right? And we say that since I naught is fixed, so there is no current that is going to flow through this particular uh, I naught. So all of your current, the whole current in the circuit should be constant. So what will happen is this current, which is increasing or moving in one direction in T1, the same amount of I current will move through T2 but in opposite direction. Opposite direction means basically negative current. Negative current means they are moving in opposite direction. And when we look into this, so if let's say I write that for T1, the current will be, it can be written as K VGS, that is VGVCN plus delta minus VS is, let's say, VX, or I say it is VCN to make the calculation. It is VCN plus VD of whole square. So for T1, the current becomes K delta plus VT whole square. Now similarly, if we write the current for K2, the I will become K into Vcn minus delta minus Vcn plus Vt whole square. So for T2, it will become K Vt minus delta whole square, right? So minus Vt, here it will be minus Vt. Yeah, so this is minus delta, this is minus Vt whole square. So this is the um, currents that we will get. Now, so this VCM, how we came to this point, or Vx is basically Vx will be the average of Vn1 plus Vn2 by 2. So from there it will be Vcm plus delta plus Vcm minus delta by 2. So that's how we come to the point that okay, this particular point is VCM voltage and it will be at VCM. So now here, that's why you can see that everything is same. It's just the direction has been changed of the current, but the amount of current flowing, the AC current is remaining constant. Now coming to our particular circuit. So if we analyze the circuit, here we have a feedback. So here we have a feedback, okay? So in our signal, since we have feedback, so this particular Vx is Vn1 or Vn plus Vn dash by 2. That is Vn. Now Vn minus, so this is Vn dash we already calculated. It was V out into 8 upon 8 plus 5 from the potential divider. And this is by considering VB equal to ground. Since we are doing AC analysis, so we are only considering the AC points. Now we know that V out by Vn is AC gain, that is, let's say AB. Okay, so and if I say my factor this R2 by R1 plus R2 as my factor A, Vx will become Vn plus A times V out by 2. Now for transistor T1, yeah, for this particular transistor T1, if I calculate the small I, ID1, it will be GM1 VGS1 plus GD VDS1. So the small current in the transistor or AC current can be simply written as GM VGS plus GD VDS. Okay. So here now considering that GD, since lambda is not given in the problem, there was no lambda mentioned, right? So we'll neglect this GD and we can write it as GM into VGS1. So ID1 is GM1 into VGS1, that is GM1 into Vn minus VS1 is this particular point. So this is source. This is drain. Vn minus Vn plus V out into A whole by 2. So ID1 is So this is ID1, that is the small current through the transistor 1. Now for T2, small ID2 is GM2 VGS2. Again, VDS is not required here. So here it will be GM2 into VG. At VG we have V out into A. This is V in dash, which was V out into A, minus Vs. Vs was V in plus V out into A by 2. So from here we'll get GM2 into V out into A minus V in by 2. This is ID2. As we discussed earlier, ID1 is minus of ID2. So from there, GM1 Vn minus V out into A by 2 equal to minus GM2 V out into A minus Vn by 2. So these two are cancelled. Okay. And let's say these two transistors are T3 and T4. And as we have discussed earlier, these T3 and T4 are mirror transistors. So if I say the current, so the current flowing through this is I1, this is I2, this is I3, and the transistor, this is I4. So in this transistor, I3 equal to I4, but I2 is not equal to I4. Okay. Rather, I2 plus I4 will become as IL, that is the load current, IL. Okay. This will behave as IL. So also equal to I1. So now when we use KCL at V out, we have I2 plus I4 equal to IL. So I2 is GM2 Vn minus V out into A by 2 plus I4 is I3, so which is Hmm. Since all the GMs are equal, so we can simply neglect this and write simple GM. But uh, this part is coming from I4. And now if we write from I2, so I2 is GM into V out minus GM I2. But this ID2 is actually minus of I2 because ID, when we calculate, ID is from drain to source current. But here we want I2 as source to drain current, right? So we need to use minus of ID. So ID2 is minus of I2. So here for I2 we will use another minus here. This will give us IL, okay? So IL will become GM into Vn minus A times of V out. This is IL. This we get from the current equations of the transistors. Now if we look at this, so this is IL, right? IL can also be written as V out upon R1 plus R2, correct? This will also give us IL, and both the IL need to match. So it will be V out upon R1 plus R2 equal to GM Vn minus R2 upon R1 plus R2 V out. So from here, separating the variables, we get V out as 1 upon R1 plus 1 plus GM R2 upon R1 plus R2 into V out equal to GM V in. So V out by V in is GM R1 plus R2 by 1 plus GM R2. Oh, sorry, R1 can. This factor was R1, right? So यहाँ पे R1 आएगा, यहाँ पे भी R1 आएगा. So yeah. Okay. So now we know that 1 plus GM R1. So considering that GM R1 is much larger than 1, we would get GM R1 plus R2 upon GM R1. So V out by V in is R1 plus R2 by R1, which is 1 plus R2 by R1. So actually what was asked in question was V out by V in, right? Which comes out to be 1 plus R2 by R1. and which is actually what, so by shortcut, luckily we got V out by V in dash as 1 plus R2 by R1. But in question, what was asked was V out by V in. So actually what you had to find out was this particular value. You see this final expression. So this is the answer. So this is how you had to solve for V out by V in. Is this clear? So basically what we had to solve was V out by V in, which will come out to be this. Okay. So I know this is very new, differential pair. This is since this is the first lecture, so you might feel a little difficult. You might feel it a little difficult, and it's a little new. There are certain assumptions that we have to take. So maybe you can go through these notes once again. And also, since I'll upload this lecture, so you can go through the lecture also once again so that there is no confusion. And if you have any doubts regarding this, we can solve them in the next session. So I hope this is clear. If you have any doubts, maybe you can stay back, or else we can meet next week. So that's all for this week.
Thank you, ma'am.
Okay.
Thank you.
Thank you, everyone.
Thank you,
So
ma'am.
see you all next week. That's all for today. Thank you.